Okay, we're talking about implicit differentiation. We've got a few things to cover. And today I will release the PSET 1, which is going to be due the coming Saturday. And yeah, that's pretty much it. Maybe there will be some changes to the PSET 1 from the official one. I don't think I would make any changes. I would see if there's a need of changes. But otherwise, that's it is. And before we leave today, we are going to talk again about the uh, problem of induction for last time, because last problem of the PSET has an induction proof, and you need to know. So
Yeah, I just read it. This makes more sense. I was a little bit confused last time, but thanks for this picture. It makes more sense now.
okay, yeah. Keep looking at it.
Yeah,
If
I'll
at
ask
the
my
end,
question again.
if you have any questions, we'll see.
Yeah, yeah. It's mostly about why this is approved, but we'll get
Yeah,
there at the end.
right. Okay. So implicit differentiation. So implicit differentiation, if you think about the term, what it means, well, implicit means something that is not explicit, right? Something that it's a thing that happens, but you don't explicitly see it happening, right? So here something similar is actually happening. So they give an example of taking the derivative of x to the a with respect to x and calculating it as a x to the a minus 1. So we did that actually last time, all right. And then now they're going to try to extend this formula or identity to cover rational a's, right? So when your a is a rational number, how do you do that? Um, well, we first try to see what it means for the identity to look like when it's rational number. A is a rational number. So we take a rational number a as m over n. Then we write y is equal to x to the power m over n. M and n are integers. Now you want to compute dy over dx, the derivative. So what you do is you say that, okay, x to the m over n can be written as x to the m x to the m raised to the power 1 over n, right? If I try to write it, this, wait, oh, sorry. Yeah, so this can be written as y equals to x to the power m taken power 1 over n. Now what you can do, you can take this inside term to be something, right? So well, we take this to be y to the n, and this holds because if you take this inside thing to be y to the n, then when you raise y to the n to 1 over n, you're going to get y back. So the equality holds. Right? Now what you do, well, you do a bit of manipulation. So y to the n is equal to x to the n. Right? So you say what you do is you take the derivative on both the sides, right? So when you take the derivative in both the sides, you're going to get n y n minus 1 of dy over dx is equal to whatever we have here. Right. I don't need to write it, but yeah, that's just taking derivatives on both the sides. So that's that. Then what you do is you just solve for dy over dx, and that's easy. That's just this, right? So Now what we do know is like y is a function of x, right? So m and n are integers. So you're doing something with x to get some value of y. That's a function. So what we do is dy over dx is equal to m over n of this. Then you replace y with x to the power m over n. So y to the n becomes x to the m over n over n minus 1. Do a bit of manipulation, not a lot. And the things that you have in the power, they get cancelled pretty soon, and what you're going to get is x to the m over n minus n over n. So that is what we need. dy over dx is equal to m over n x to the m over n minus 1. Now you would ask, like, why wasn't this sufficient? Well, this wasn't sufficient because we wanted the derivative of y with respect to x to have everything in terms of x. But we had y to the n here, which was the pain in the neck. So to get rid of the y to the n, that's why we did all this trouble, right? We replaced y as x to the m over n, and we went through the trouble to get it all in terms of x, right? So that is pretty much what we wanted to do. Any questions?
No, thanks for the last part. It was clear. Thanks.
Okay.
Yes.
Now we're going to see something else. So we know that the unit circle can be written as x squared plus y squared equals to 1, right? And well, what you can do is you can have it as an equation of y with x. So you write y squared is equal to 1 minus x squared. Okay, so what is y? Well, y is plus minus square root of 1 minus x squared. So you look at both the cases. The positive cases when the square root is positive. So y is equal to positive square root of 1 minus x squared. So this is 1 minus x squared to the power of 1 over 2. Okay, now you apply the dy over dx formula that we just derived to this. So you get 1 over 2 times 1 minus x squared to the power minus 1 over 2 times minus 2x, just by doing all this. And what you get? Well, you get this minus x over square root of 1 minus x squared, 1 minus x squared, and 1 minus x squared square root is just y. So this is minus x over y. So this is just like directly putting the formula and getting the answer. But if you deliberately try to use the implicit differentiation kind of idea, you say that, okay, x squared plus y squared is equal to 1. Now if I write d over dx of x squared plus y squared, so I'm taking the derivative of that with respect to x, and I take the derivative of this, so I'm taking the derivative on both sides of the equality, and the right hand side is going to be equal to 0 because 1 is a constant, and the left hand side is going to be by the summation rule, which is going to take the derivative of each of the terms. Now what you do, well, you have to be kind of very, very careful with this. This thing turns out to be 2x. This thing doesn't turn out to be 2y. Right? It's not. But it is 2y times dy over dx. Right? Why is this so? Because you're not taking the derivative of something which is a function of x. It is not directly a function of x. Right? It is first a function of s, then you have this y itself alone as a function. So first you do the derivative of y squared as if it's a function of x. So you get 2y. Then, again, according to the chain rule, you're going to have dy over dx, right? Because that's the other function in the composition. So this turns out to be 2y dy over dx is equal to minus of 2x. dy over dx is equal to minus of x over y, which is what we got, right? So it's not the technique itself which is like the most important, but it's the idea of implicit differentiation, right? So okay, I would like someone to explain me again why when I take the derivative on both the sides of this, I get ny n minus 1 times dy over dx. Yeah, just someone explain me.
Can I try?
Yeah, sure.
When we take the derivative of both sides with respect to x, so we take it at d upon dx, and in the both side y raised to n is equal to x raised to m. So while differentiating, while we are differentiating with respect to x, so we cannot directly apply it to y. So we use the chain rule here, and d of y raised to n dx, and we multiply it by dy upon dy, which is essentially 1, but we will it is essentially 1, but we will rearrange it so that we get dy by dx, and we will differentiate the y raised to n term with respect to y, and we will get ny raised to n minus 1 into dy by dx. And on the other side, we were differentiating with respect to x, so there was no problem. And the m term was so the difference after differentiating with the rule, so we got mx raised to m minus 1.
Right. That's spot on. Something that I would like to emphasize on what he said was this. Said you write the right hand side as dy to the n over dx times dy over dy, right? So what happens? Well, you apply the chain rule. According to the chain rule, this is equal to dy to the n over dy times dy dx. Sorry, this is bad handwriting, but yeah. This turns out to be exactly this, ny n minus 1, and this is exactly this, right? So I hope this made it more clear why implicit differentiation matters and what it actually does.
I'm trying to figure it still out. Wait.
Yeah, go on. Think about it, ask anything.
What are you doing? Dy. Yeah, dy over dy. What
Yeah.
is that part?
That is essentially equal to. Sorry, this is
Why
essentially.
dy over dy?
This is just 1, right?
Yeah, but why? Why over dy? Where's it coming from? Maybe I'm missing it.
No, it's just that like you can write. It's kind of a algebraic manipulation.
Oh.
It's just writing the same thing in a different way so that you can the chain rule. There's a chain rule. So like the idea is, do you see this? The implicit word comes from the fact that this derivative was essentially hidden, but we pulled it out of thin air. See?
Yeah, exactly. Okay. Yeah, thanks.
So yeah, this is basically just rewriting into the same way so we can use this and then some manipulation. But one must realize that you don't just ward it off as obvious, because it not really is.
So I just checked out the quartic formula.
Which formula?
The quartic formula.
The quartic formula?
It
You're
was
talking about the x to the 4, the degree 4 equation?
yes. In the lecture it was. In the lecture the quartic formula was not there, but but he referenced it that it was some really dangerous formula.
It is.
And when I looked out, it was some really long equation. You can also see it in chalkboard. No, you can just download it.
Oh,
The
okay.
SVG file.
The SLG, I see.
It is really wrong.
It's not open. But the thing is, like, I know the quartic formula. I've tried to do it myself when I thought I could do something, but it was like just wasting time trying to do algebra. Yeah.
Yes, I can share the statements.
Can I ask a quick question about implicit differentiating again? Is it? Can you say that it is the chain rule, but it's just expanded to also use it for y? Is that just the only difference?
No, the thing is, implicit differentiation means it's not necessarily about the chain rule. It's just that somehow the chain rule helps you do that. You don't really need the chain rule. The thing is, how can you write this in terms of like a differentiation, right? Yeah, some kind of differentiation. Not the trivial one. The key difference between the left-hand side and the right-hand side in this equation is that y is not directly differentiable with respect to x, right? So you need to see what's like being stuck. What's being stuck is essentially there's this implicit derivative in there which you need to pull out and then apply the chain rule so that you can get this. That's the main thing. If it were like y to the n instead of y to the n, it was like x to the something else. You don't need this one. So yeah, that's just basically. I would recommend you to look more into implicit differentiation. I believe Stewart's, if I have the book, yeah, I guess, yeah. His book had a good chapter on implicit differentiation, if I remember. And this book is actually of our level. This is not like Spivak, like something out of the world. So you can check and practice from this if you're interested. But regarding implicit differentiation,
can you send it maybe?
Yep, yeah, I think it's a bit large in size. We'll have to see. Yeah, but I'll put it in the Google Drive I have.
Okay, good. Thanks. Are there also practice questions and answers there? Because I'm still looking for one place to do exercises.
Yeah, this
Oh, sweet.
has exercises, a lot of them.
Oh, that's perfect.
And it has probably,
Yeah.
if it doesn't have
Solution?
solutions, you can look for it online. He probably published another book for the solutions. It's like 1,000 pages long, so yeah.
Okay, I'll look those up then. Thanks.
Yes, I'm trying to look where the implicit differentiation was.
One of the death traps for me is like trying to find the perfect book or perfect place to study.
You're not going
Is
to
this
get
better?
but the thing is, Stewart is like a classic. Again, the thing is, when you're starting with the beginner materials, you don't have to choose from a lot, because the thing is, it has been taught so many times over the years that every book is standard. Like, it doesn't have anything out of the world information, right? So if you can get a book which covers most of the topics you need, and it has enough amount of problems, that's good. Like, so that's the thing. I was like confused, like which book I should try, which book I should not. But I just decided, okay, I'll just stick to this book and I'll get it done. Of course, it has its flaws, but I'll nonetheless learn something. And it's enough, because most of the books are essentially the same.
Okay, yeah. I'm still struggling. Even with physics one, I'm still my planning. I just can't make it. But
With physics one, of course, he messaged me. I didn't get back to it, but I started back when I did physics one was from 801, but I didn't spend a lot of time doing 801 lectures or anything. I spent a lot of time with the P sets, and the book that I followed was Halliday-Resnick. Halliday-Resnick. It's essentially the same as University Physics, Young Friedman, but it covers a few more things or something like that. So I would say pick up one of those thick books, the University Physics or Halliday-Resnick, stick to it, and don't do all the problems. You're going to die. Do pick problems, pick problems which look interesting and which you can just leave. Like, the thing is, again, you're in a chapter, you're going to have hundreds of problems. How do you choose? Well, you do 10 problems from the beginning and 10 problems from the end, and maybe 5 problems from the the rest. You'll see, you'll get an idea about how the problems look. Because again, the goal is not to finish the book cover to cover. The goal is to learn enough from the book, right? So.
okay, I'll ask my last question in the PM because I don't want to hold everyone up. Let's go.
If university physics is more available than Halliday-Resnick, then can I opt for it?
Yeah. I think I got Halliday-Resnick on Amazon, like for I'm talking about Indian rupees, INR 800 or something. But if you're getting university physics cheaper, go for it.
I saw, but it has rised, I think. Halliday-Resnick.
I see, Amazon.
Yes, no, Halliday-Resnick is expensive and university is cheaper.
Okay. Take university physics. They're basically the same. They cover things that they both like at the same level, which is freshman physics.
I heard from somewhere that Halliday-Resnick is more on the tougher side.
It is a bit on the tougher side because university physics like doesn't have a lot of the quantum mechanic things, I believe, but Halliday-Resnick has something like that. But don't worry about that. Like, it's fine. There's not a huge difference. It's okay.
Thank you.
Yeah, because again, if you're going to like get into those problems, you're never going to be able to choose a book. So.
Yes.
Again, okay, so this is what I wanted to show you, implicit differentiation in Stewart. Check it out. He gives a very nice example for this. For example, this thing, the volume of Descartes. This is a very interesting thing. Try this in Desmos and you'll see how cool it is. And This has something to do with implicit differentiation. So check it out. Probably it has more material than lecture is going to cover. But it's at the same level as we're doing so. Let's get back to our stuff. Inverse functions. Okay. I hope everyone remembers when we talked about functions, surjective, injective, inverses. So can someone tell me what an inverse function is?
I think for inverse, when we invert the y and x and we define it like that.
So is sine inverse of x equals to 1 over sine x?
Can you repeat, please?
You said inverted. So is sine inverse of x equals to 1 over sine x?
No, I mean tan inverse of x means actually when we have the value of sine and we have to find the angle, and when we have the value of sine and we have to find the value of angle, then we use sine inverse.
Right.
Am I right?
Right. But the thing is, what is the sine inverse? How is it related to sine?
Earlier we had y equal to sine x. Then earlier we had the function y equal to sine x. But now we are putting y in the sine inverse function, and we will get the value of x.
Right.
The corresponding value of x.
Yeah. So basically, what the inverse means, if you go back to the lecture 0 notes, I think I might not have put it, but again, I talked about bijective functions. Bijective functions have inverses. So inverse just means so that when you compose the function with its inverse, we're going to get the original value back. See? So f of x composition f inverse of x is going to give you 1. Right? It's the identity, because you're on both the cases you're calculating x, right? But instead, if you have something like this, so you have y is equal to f of x and g of y is equal to x, right? So now be careful what we're doing. Y is a function of x and g is a function of y, which is equal to x. Now, what does this mean? Well, what this means is when you put x equals to g of y in here, so it becomes y is equal to f of g of y. And what does this mean? This means that g is the inverse of y, because again, how I said, if the inverse is something when you take the composition and it gives you the same thing back, right? So if I try to write it, it means that f of f prime of x is equal to x. And if it happens for all values of x, that's what means it. What does these brackets mean? They mean that you do f prime first, and then you do f. So this is f composition f prime. And what does this give you? It gives you the same thing. This is equal to the identity function. I don't think I told you about the identity function, or did I?
I haven't heard about the function. Can you
No, me neither.
Okay, I think in the lecture 0 we messed it up. So identity function is nothing but it's a function that goes from the same set to the same set and takes the same element to the same element. How boring. It is essentially, it creates a copy of the same element, right? So it's the identity. So how is this helpful? Well, when you're talking about a lot of maps, this map stands out as a special one, right? Because it keeps the elements fixed the same. So what happens is the inverse is the function. When you take the composition with respect to the original function, it gives the identity. And what does that mean? Well, it means that when you're evaluating with respect to some x, you get always x back, because that's what the identity function does. It takes an x, and it always gives you the same thing back, right? So that's what the inverse actually means. It means that when you take the composition with respect to the original function, it gives you the original thing, original value. So how do we go from here to where we were? Well, so here, what this means, this thing, this this setup, what this means is that y is equal to f of g of y, right? Because that's what we have set x to be. G is a function of y, and that is equal to x. So g happens to be the inverse, as we said before. So what we do, well, we try to do the same thing as we did to get the derivative of the inverse function, right? Which by trying to use the inverse, like the special thing about the inverse, right? So y is equal to f of x. F of inverse of y, what is it? It's x, right? Because it gives you the same thing back all the time. So f inverse of y is equal to x. Like, Siddharth said, sine of x is equal to some y, then sine inverse of y is going to give you the x back, right? So what we do, well, we try to take the derivative of this inverse that we got. Okay, so d over dx of f inverse of y. What is it equal to? Well, it is equal to the derivative of x. And the derivative of x is 1, right? Well, okay, so now we're not yet over. Right? We say that this thing, d dx of f inverse of y, is actually equal to first taking the derivative with respect to y, and then having dy over dx. Do you get why we did that? Just like before.
Yes, we could not differentiate it in terms of x.
Right? Yeah.
So we multiplied again dy dy.
Calvin, you sure about how we did here?
I think, yeah.
Okay. Okay. So that's what it is. Then what we do is we take dy over dx to the other side. So we get d over dy, so the derivative of f inverse of y with respect to y is equal to dx over dy. Right? And that's what happens. So implicit differentiation helps you with calculating the inverse of the functions, and this is phenomenally helpful when you're dealing with trigonometric functions, as we are going to see here in a minute, because trigonometric functions have the arc functions, the tangents, and all of those things. So when you're trying to find the arc tangent of x, what do you do? Well, you first say, okay, tan y is equal to some x. Now you take the derivative of tan of y, tangent of y. You use the same trick as we did before. Okay, so this is equal to 1. We know what the derivative of tangent of y is. Well, if you don't, maybe we're going to see later. But yeah.
X square.
Sorry?
X square x.
But yeah, basically we try to get dy over dx by using the same idea. And then they use some geometry to simplify.
Well, we can also use the quiescent rule on sine by cos.
function g is an inverse of f if g of f of x is equal to x. No, because when you're talking about the inverse of a function, you apply the function to its inverse, right? So it's going to be f of g of x to be equal to x, not g of f of x.
Wouldn't it be true?
No, this, if g of f of x is equal to x, then this means f is an inverse of g. Those are two different statements.
I will review it once again.
Yeah, like it depends on the order because as I said, when you're talking about inverses, always think in terms of the composition, and f composition f prime is not the same as f prime composition f, right? So if your f prime is an inverse of f, this is going to be your identity, but that doesn't mean this is also an identity. So f cannot be an inverse. So you have to check both the things.
Yes.
And this geometric explanation, is everyone good with this, or do you want me to explain? It's basically just trigonometry applied.
Yes, I am good.
Everyone else good with this too? Calvin, you good?
Yeah, I'm looking at it.
Yeah, look at it and tell me, yeah.
Right now, what they're saying here is the triangle is triangle of y is x. So x over 1. I guess so. What did it show here? It is inverse function.
So the goal is, we use, again, this helps you because once you have this as 1, a lot of things cancel, a lot of things simplify, right? So tan of y is equal to x, right? So y is again just perpendicular over base. So it's going to be x over 1, it's going to be x.
Yeah.
So arctangent of x is going to be y. That's the definition of arctangent. Right? You good on that?
Yeah, it's the inverse. Sure.
Yeah. So arctangent is just the inverse of x. So as we said, it's going to like sine. As I said, sine of x is equal to y, and sine inverse of y is equal to x. Right.
Yeah, I'm just trying to figure out what is the formula for that. I mean, if you say sine, sine is opposite divided by hypotenuse.
Yeah.
But what is the inverse of?
Remember what we're doing here. Tan of y. So when you're taking sine of theta, theta is an angle. That gives you sine theta is equal to perpendicular over hypotenuse. There are two different things. Theta is an angle, perpendicular and hypotenuse are sides. So when you put that value, when you get from the fraction into the sine again, so you get sine inverse of perpendicular over hypotenuse, you get the angle back. So you're going to get something in terms of radians or degrees. Do you see that?
Yeah.
Right. So
but what does that mean? Yeah. If you sketch it out,
sine theta.
You put an angle in, you get a
Right.
ratio.
Right. So let's say
the inverse.
Let's say, okay, let's pick an angle of theta, sine 30. Okay, sine 30 degrees, pi over 6 is equal to 1 over 2, right? So we say sine inverse of 1 over 2 is equal to some value of theta. And as you can guess by the fact that this is a sine inverse, this is equal to pi over 6 or 30 degrees.
Yeah, but what is the formula for doing that? Or isn't there a formula?
You don't necessarily have a formula. Like calculating the sine inverse is through the sine, basically. Because sine inverse is not a function, like a new function itself. It's something that is an inverse of sine, right? So,
yeah, but what is the function of sine? What is...
again, like you calculate sine theta, you get some value for it, then you say, okay, so what is the inverse when you take this value? So I think if you intend to look for it, I guess, yeah, normally some trigonometric courses in high school, they don't really teach inverse functions. That's pretty bad of trigonometry.
I think only Taylor expansion is available for it. It gives just an approximation.
Yeah, that's true. But if you intend to look more on it, let me see. I think the inverse functions were also in this book. And if you don't find anything good, we can always talk about it. Yeah, okay, so inverse functions, log, do they have sine? Yes. So check this out, inverse trigonometric functions, James Stewart, calculus. Right after today's lecture, I'm going to post the PDF. And this one, that's why I made it clear, right? Sine inverse over x, inverse of x is not equal to 1 over sine x. Think a bit about it, try to see the graph, and if it makes sense. And there's nothing interesting about it, it's just some manipulation. So, see it, and if you have any doubts, feel free to ask. Okay?
Okay, thanks.
Sure.
We're going to need for sure. Inverse is going to be needed. Hyperbolic functions are going to be needed everywhere. Like if not in calculus, you're going to need it in linear algebra and whatnot. So do it. Yeah. So what he did here was basically you have the arctangent. You get something for the hypotenuse. So the hypotenuse is equal to root over 1 plus x squared, of course. Then what we do is we say, okay, cosine of y is equal to 1 over root over 1 plus x squared, b over h, the base over hypotenuse. You find cos squared of y. Okay, cos squared of y is this. So dy over dx, dy over dx is basically 1 over 1 plus x squared, right? And that is equal to the derivative of the arctangent. So how you find the derivative of the inverse functions, inverse trigonometric functions, is through applying the implicit differentiation on the original simple trigonometric functions that we know. I'm not sure how he covered this in the lecture. Did he explain it well?
Which part?
I mean, yeah, the geometric intuition and everything else. Did he explain it well in the lecture?
Yes, yes.
Okay.
I noted it too.
Okay. So here's a bit of an idea about how to graph inverse functions, and this is a good thing to think about for sure. So I'll just give a brief idea about how to do it. So if you have a function y equals to f of x, g of y is equal to f inverse of y, it's x, right? That's the function of this, the inverse of a function. Now to graph g and f together, we need to write g as a function of x, right? We need to, because again, when you're putting things on the plane x, y, if you write one thing as a function, you need to have the other thing as a variable, right? The parameter. So if we have g as a function of y, but we need to put it on here, we need to write it as a function of x. Right? So we say if g of x is equal to y, then x is equal to f of y. You see why this is the case? Do you understand? Like, why we can write g of x, if g of x is y, then why can x be equal to f of y?
Yes.
Yeah, the y of g is the x of f, something like that.
No, no.
I mean, not literally, but
You have to think again. What happens when
output.
we replace y with g of x? It becomes f of g of x, right? And if that
Yes.
is equal to x, then that is good, because as we said, g is an inverse of f, so that happens. That should be true.
Since f of x is equal to y,
Right,
and then when we put the value of y in the inverse, then we will get x.
right. Always think about this in, like, when you're talking about inverses.
Then isn't the question asked earlier was true?
Sorry?
The question that Jose asked earlier, isn't it true? Because I am also seeing both definition here. F of inverse of f of x is also equal to x, and f of inverse x is also equal to x.
Yeah, that's because, again, it's a well-defined inverse, right? If you don't have a well-defined inverse, you can't say in both the cases. So here it happens to be the case, but it's not always that the inverse would give you that.
By the way, the definition of well-defined would be here like, I mean the meaning of well-defined here in this case.
The well-defined inverse is that the well-defined is it happens in both directions, right? So
No like this, no discontinuity.
yeah, not discontinuity in the sense that, okay, so here's the thing. Let me do some set theory functions for 5 minutes. So if f is a function from a to b, f prime is a function from okay, we have the function from b to a.
B to a.
Right. Okay. So we say that be careful with the choice of words. So f prime is a function of is an inverse of f. Well, what does that mean? It means that when you first do f prime, you go from b to a. Okay, we did f prime. We went from b to a. Then you do f with it. You go from a to b. What happened? You came back to b. Right? So this is equal to the identity on B. What does an identity on B means? It just means the map which fixes all elements of B. So it takes the same elements of B to the same elements of B, right? This is just one condition for the inverse. You say it's f prime is a well-defined inverse when you do f first, you go from A to B, then you do f prime, go from B to A, and that gives you what? The identity should be on?
A.
Right. This needs, this is necessary for a function to be a well-defined inverse, right? And this is not always the case, but again, for our course, we can assume that, but I'm just saying, when you deal with functions later, that's not going to be the case.
Yes.
Okay, I hope that was clear. Give me a second. I'll just need someone's knocking the door. Okay. So how do we graph this? Well, how you graph this is first you say, okay, g of x is equal to y. Okay. So alright, g of x as a function, like we write any function, we make a graph. So this is your graph of g of x, right? Now what you do is you try to rotate this graph. So if I try to rotate this, actually, no, not like this. Yeah, like this. So what you do now is you're now trying to find f of x as a plot, right? So it's going to be inverted, right? Do you realize why it's inverted? Because we literally rotated the coordinates to find the graph of that, and that's gives you the inverse.
I think you turn on the inverse of your screen.
Yeah, that's what I did. That's to show that this is.
Okay.
Yeah.
Oh, sorry. sorry.
Does the point where the graphs would meet have some special significance?
The point where the graphs would meet would be the value for which the inverse and the function give you the same value. So that would be in sine. What would be that? 45. Sine pi over 4. See, it gives you no, not that. Sorry.
Somewhere where the angle and the sine are nearly equal.
Yeah. Sorry, not that. I think you'll have to look at the sine graph for that.
Sine 0.
Yeah, it's sine 0. Yes, obviously.
So that's where the both graph is made.
Yeah, the inverse and the function, they both give the same value. Okay. As I said again, look more into inverse of trigonometric functions in Stewart's book. You would probably get a better idea. And any questions, you can always ask. So, would we want to talk a bit about last proof before we leave? I think we're pretty much at the end. Anything about last induction proof last time that isn't clear or you would like to know more?
Oh yeah, let me see. Wait.
I think I have to try it once more again. Then I will ask.
Sure, yeah, try it. Try this, or try to look up for calculus identities of derivatives and try to prove them on your own using induction. Induction takes practice. Yeah.
Yes. I had done the induction part of mathematical circles, but some exercises remain. But I had done that earlier.
I see. I think I did induction around the same time too. When I was doing number theory for computer, sorry, math Olympiad. It needed a lot of induction.
Yes. And the Tower of Hanoi and some puzzles like that. That also uses induction. What is the Tower of Hanoi?
Yeah, go on.
Is the Tower of
Is he in the middle of a question or?
Oh, sorry. What you were talking about? Tower of Hanoi?
Yes, sir. Is the Tower of Hanoi? Why is the Tower of Hanoi such an important problem in computer science? Beginners.
I wish I knew the details. I don't. But maybe we can continue this later when I probably have something else to see. But it's probably about the number of something related to 2 to the n minus 1, right?
Yes.
So that is related to the Fermat's little theorem, if you know. It looks a lot like that, but something about it.
Yeah, I will try it.
Okay, Kelvin, go on.
So when you come to the end, at the parts so we have, now if you work it out and you get to minus n minus 1 over x to the n plus 2, how is this a proof for that 1 over x to the n is minus n x to the n plus 1. How is this a proof for that?
And that's the whole point of induction. Again, what is induction? We start
You're trying to prove it for n
n plus
plus
1,
1.
right? We did it for n plus 1.
Yeah.
So
And then you work this out.
Yeah. So again, that's the trick of induction. You say that if you can go from assuming that it works for n and you show that it works for n plus 1, that's it. You can just say by induction it works for every n.
But you get to minus n minus 1 and x to the n plus 2.
Oh no, okay, wait. This should be a typo, or where is it? This should be minus n plus 1, right?
I don't know.
Wait. Let me check it, God. D over dx. Oh no, this. Minus n minus 1 over x to the n plus 1. So it's going to be n plus 1 plus 1 n plus 2. Yeah, I think it's correct. Like, where are you stuck?
So it was correct?
Yeah, I mean, think about it. The formula says d over dx of 1 over x to the n is equal to minus n over x to the n plus 1. Right. Yeah?
Yeah, you gotta
Okay.
prove that.
Okay, now we say d by dx of 1 over x to the n plus 1. So we replace n by n plus 1. So what we are going to get? Minus of n plus 1 in the numerator. In the denominator, we're going to have x to the power of n plus 1 plus 1. Right? That is n plus 2. So minus n minus 1 over x to the n plus 2.
Yeah, that's correct, but the upper part, minus n plus 1, right?
Which one?
The upper part, n minus n plus 1.
That should be plus. Yeah, the fraction between those
Oh,
two, that should be plus. Yeah, that one.
Oh, okay, then I get it. Then I think I get it.
Because the previous part has the plus, right? I don't know why I wrote minus there. Just above it, it has the plus between those two.
Yeah, exactly. Okay, thanks. I think I get it.
Okay. Yeah, if you don't try to practice something, yeah. Okay. I hope we are good on the things for lecture 5, and I wish everyone good luck for the PSAT 1, which is going to be due on Saturday. You might have to struggle a bit for this one, yeah.
Thanks. Is it true the last one is only one lecture, and then the exam is due?
If I remember the schedule, after implicit differentiation, we have an exam, yeah.
Oh wow.
See how it is.
Yeah, for the 1801 SC, you have a whole another week, I think. There's like 7 more.
Do we have another PSAT before the exam? Okay, then
at
we
least
probably have an exam. Because we're going to spend another lecture on review, right?
Wait, let me check.
Yep. So here's what we have. Today was lecture 5. Coming Sunday would be lecture 6. That's the exponential and log. And then next Monday would be exam 1 review. So I will be reviewing last 6 lectures or last 5 lectures, whatever. Then on Saturday, we're going to have the exam. Instead of the PSAT discussion, we're not going to have any PSAT for that week. We're going to have the exam. Okay, looks good.
So how many? It's not next Saturday, but
Yeah,
the one
it is
after.
next Saturday.
Oh, okay.
Yes.
Sure.
Again, it's just 5 lectures. It's not a big exam, and the exams are going to be less difficult than the problem set. I can bet you that.
Okay, perfect. Thank you. I see you next time.
Yeah.
Can
See
I
you
ask
then.
something?
Bye bye.
Oh yeah, you have a question? Sure, I'm around.
Just a polynomial one. If we have some general polynomial and we put some value x and get some value on the other side, and when we have that the value of y, and then how will we form an inverse function? An inverse function which gives the value of x for every such value of y.
Okay, let's try to think about it in terms of like an easy polynomial first. So let's say f of x is equal to 2 plus x. Okay? Then you try to write, okay, for what value, sorry, how can I write x as a function which when I put it is going to give me back 2 plus x or x back or whatever, right? So you have to think of another way to write x. Okay, so if I write x is equal to some function like let's see, 2 minus x? No, not 2 minus x. Let me try to explain this. F of y is x.
Well, for linear function, we could just directly.
Right, that's the thing.
We could just directly perform the operation of y. But on some complex functions which have a degree order,
you'll have to. That's the same thing as trying to find inverse of like sine squared x or something like that. You'll have to be careful about taking the power of the inverse. I would say that there's not a like direct formula for this, and almost always you will have to compute. But again, the thing is, most of the time you don't need one. You don't need an inverse function of a polynomial, because in polynomials we care about roots, right? What makes the function go to 0, not another function, because that complicates things, right?
Yes, and I wanted to ask last thing, right? What's it? I saw George Simon's on PDF, but if I want some if I want some book which I can keep, like some hardcover book, hardcover, then which book should I prefer usually for calculus?
For calculus,
right?
Let me see. I'll have to check Amazon and the prices now if there's some decent price of Thomas.
Some which I saw were some like Thomas calculus and some others.
Right, Thomas. How much is that?
It was around 800 if I last remember.
That's good. If it's around 800, take Thomas calculus. Thomas calculus is going to stick with you up until differential equations like 1801, 1802, 1803. Thomas calculus is enough.
So would it be, if it is, the price is actually 749 now, I checked. So So would it be great book?
It would be. The thing is, again, Thomas Calculus is good because it has both explanations and a lot of exercises, right? I didn't learn a lot of my calculus from Thomas. I practiced some. I didn't learn a lot. Nor did I learn vector calculus or multivariable calculus from here. I learned that from other books for like physics. But if you want to learn it in this way, Thomas Calculus is a good book. It has all the topics that you would need. So, what other options do you actually have instead of Thomas?
I have not checked that, but I had heard about this, so I just asked.
Yeah, so Thomas is good. Yeah.
And then there was some Calculus 10 by Horvath Anton.
I've not about it.
Then there were some Indian order version, but they are all oriented only for G Advanced. But I just wanted some general book.
Right. That's the thing. I learned calculus when I was like in grade 8, and my sister was like having those JE books on Amit M. Agrawal, if you know his books, on
Yes.
integration and differentiation, and that's how I taught myself for the first time calculus from those books. Then I went to other books. Yeah.
So should I take Amitabh Agrawal first?
Sorry?
Should I take Amitabh
No,
Agrawal?
don't do it. I regret. If I had better books, I would go for them. That's the thing I knew. That's the thing I had at my as my option. So that's what I did. You have better options to do them.
So compared to Thomas or other books, it is not that good, right?
Amit M. Agrawal?
Right?
No. Again, because like Thomas's calculus or like Stewart's, they're written for university students specifically with the intention of explaining the concepts, not for some specific exam. Right? Most books of Amit M. Agrawal are for J Advanced, and all they do is teach techniques. So I think what I learned from Amit M. Agrawal, R.D. Sharma, all those books when I was first starting calculus. Those were all my sister's books. That's why I did them. But I learned computation and computing things very easily from them. But I didn't learn the concepts that well until I saw them elsewhere. So I would say start from here is better. And if you need computation, you can always go back.
Which computation?
Sorry?
What you said last line? Computation?
For computation, you can always go back. If you have the concepts right, for computation, you can always go back to some other book.
Right. What I particularly saw was these books which were some exam oriented are not as well written as some which is general perspective, I think.
Right. That's the thing. That's why I have so much hatred for Indian education and J in general. So you don't see.
By the way,
Sorry.
By the way, where do you live?
I live in Odisha, Bhubaneswar.
I live in Gujarat, by the way.
Gujarat. Ahmedabad?
Ahmedabad.
Ah, yes.
Right.
Majama.
Maja.
Okay, yeah, try Thomas's calculus is good. Don't try Amit Agrawal. It's not good. And yeah, that's the thing. This course that we're doing is going to be much more helpful than any other coaching center or anything that they're going to teach on calculus for sure. So.
Yes. Thank you very much.
Okay, yeah, I was glad that we had the discussion. Next, I'm going to post the preset now, and we'll discuss it Saturday.
Yeah.
Okay.
Bye.
Good evening.